First of all, I have to apologize a little bit. You see that I have a muscular issue, and hopefully next Monday it will be solved. Okay, so don't be irritated. Therefore, I will not walk so much, talk so much as I do it usually. A few words about me. I'm a software developer since the last millennium. Yeah, right. It's the way. Since 22, 24, I give classes. I started with Python, then I gave classes for my company, worldwide classes. 28, I gave worldwide remote classes. By the way, this was terrible. And since 2016, I'm an independent C++ trainer. And I also give C++ Python classes, but only 10 a year. Okay, I also have an international mentoring program running, which takes place tomorrow. So this is a little bit of my background. So let's talk about concurrency. Concurrency improvements in C++ 20. And I will not talk about so many features, therefore I can dive a little bit deeper. So this is what I talk about. Atomics, and I will also give you a little bit of background, what we got in C++ 11, how it's improved in 20. I will talk about semaphores, latches, barriers. This is totally new in 20. About cooperative interruption. And finally about jthread, the improved thread. This is all for today. I will also include the exercises in this presentation. Therefore, when you want to have it, you have it included, because there's a link to a Gottbold compiler example. Atomics, a little bit of background, are the foundation of the memory model in 11. They define operations on them are atomics, clear, this is why they are called. And additionally, they define synchronization ordering constraints. This is, for me, the more interesting parts. And the interesting part about atomics is these ordering constraints also apply to non-atomics. Once more, to non-atomics. Okay. To make it short, when you do something with non-atomics, and you do some kind of synchronization, it boils down on a synchronization on atomics. Therefore, atomics are the pillars of concurrency. Meaning, condition notify one synchronized with a condition notify wait, notify once or notify all to be precise. Unlock synchronizes with the previous lock call on mutex. Thread creation, thread joining is a synchronization point, and so on and so on. So they are really, really important. And this is what we have in C++ 11 and 20. We have the atomic flag, and we have stood atomic and various specialization of it. Stood atomic flag is an extremely, how should I say it? It has no rich interface, let me put it this way. You can only do two things, clear and test and set. With clear, you put it in a kind of a false state. With test and set, you put it in a true state, and you get returned the old state, if it was false or true. But stood atomic flag has one extraordinary feature. It must be lock-free. For all the others, stood atomic in its specialization, they can internally use a locking mechanism. We don't know it. We only know it for the smart pointers so far. So we have stood atomic specialization for pointers, for integral types, for user-defined types if they are simple enough. For floating point types, this is new with 20, and for smart pointers. And for smart pointers, so far, each implementation uses a locking mechanism under the hood. This is still a fight to get them lock-free. Daniel, you are involved? No, this is a hard fight. Yeah. And this is what you can do. With stood atomic, you can say test and set or clear. You see, you can not even say on an atomic flag which value do you have. To get the value, you have to change it. You have to set it. So it's pretty yeah, how should I say it? Not so convenient, but powerful. And then we have operations on atomics. Not all of them are available for each type, but this is what we have. And I only want to give you a little bit of background, only want to talk about this operation here, compare, exchange, strong. In short, often called CAS, compare and swap. This is, I would say, the bread and butter of atomics. It's a little bit complicated. Here you see it. What you can do is the following. You check if atomic is equal to expected. If yes, you set in an atomic step atom to desired and return true. If no, something may happen in the meantime. No, you set expected to the new value of atomic and return false. So essentially, there are two operations in one, and you return if this is successfully or not. And what I do now is implement for you with this fetch add atomic multiplication, fetch mult. You see we have fetch add and fetch sub. They return the old value. And this is what my fetch mult also will do. Have a look. I use compare, exchange, strong. I assume this is big enough for you. Only the people from the last row count. Okay, you see, I have an atomic here, and I want to multiply it by 5. This is what I want to do. Can't you see it? Is it now better for you? Okay, thanks. Okay, and this is my fetch mult. It takes this atomic T by reference in this mult I want to multiply with. And what you do essentially is always kind of this thing. You load the old value, and then you apply in a loop, compare, exchange, strong. And you see this is a loop. This loop continues as long as it returns true, right? And what is happening here? You compare in an atomic operation the shared value with the old value. If both values are equal, you know your observation of the world is right. Now you do in the same operation update shared with old times mult, because you want to multiply. And you return true, therefore you are done. And you return old value. If not, because something changed in the meantime, this function could be used by many threads concurrently. You change the view of your world. You change the value of old value to the updated value of shared, because someone changed it in the meantime. And you do it once more because you return false. You do it until it's successful. You don't care when your call is successful. You only care that it will happen in some point in the future. And this is how you should look at it. This is for me an atomic transaction. You store the state of the world, then you hope to perform an operation. If not, you do it once more. This is how you do software transaction memory, probably in the 26, or how you would do a database transaction. It's a kind of an atomic transaction. And the key part is compare, exchange, strong. Sorry, this was a little bit a wrong story because this was C++11 related, but I want to give you a little bit of background. Okay, let's jump back.
But you should make sure that the multiplication is not undefined behavior.
Yeah. Can you elaborate more on it, Daniela?
Because if somebody changes the current value of the shared atomic, and you don't take this into account for the multiplication, you run immediately into undefined behavior, and this is probably not what you want.
Okay, let's analyze this later a little bit deeper. Okay. let's continue. And now what we get with 20 additionally. Atomic flag, and on atomic now you can notify. You can wait on it, and you can notify one or all, similar to condition variables. And this wait works a little bit special. This wait blocks if the value for atomic is equal to value of val. Keep this in mind, because I will show it now to you. So it's a little bit special. So it blocks if val is equal to atom. And if not, it of course not blocks. Don't blocks. Let me see how I can use this to implement a simple producer-consumer workflow. I have a thread waiting for work, and I have a thread set data ready. Set data ready prepares some work. Here we are. Prepares some work, puts a few ints onto a vector, which is of course not thread safe. Says data prepared, then stores true in it, and then says notify one. Initially, it has the value false. This means this guy here is blocked because it blocks on false. It blocks until this guy puts the value true to it and notifies the other. This is a simple producer-consumer workflow based on atomic bool. Keep this in mind because I will give you a few performance numbers, but I need a little bit more of theory now. Do you know why I explained this so deeply? Because I'm a big anti-fan of condition variables, which I will come later. Okay, we have atomics. We have a shared pointer. And shared pointer have one big issue regarding concurrency. Do you know my favorite quote from Tony van Aert? Of course you don't know it. Forget what you learned in kindergarten, don't share. But shared pointers share by design. And there are two meta rules when you do concurrency. Don't share, don't mutate. And they share by design. Therefore, they need our extremely specific concurrency semantics. And now with C++20, we have new specialization to the atomic for shared pointer and weak pointer. Here's a rationale from Hubsutter why we need them. You may not know it, but shared pointer was the only non-atomic variable in C++11 on which you could apply atomic operations. So out of consistency, we need it. Second, out of correctness reasons, you can say atomic store shared pointer. This would be fine in C++11, but you can easily forget it and do it this way. And now your program runs, but you have a data race. And third, we could also make the shared pointer by design thread safe. But now we would optimize for the not common case, which is bad. Therefore, we need it. I like this explanation or this rationale from Hubsutter. Okay, we have also in C++11 atomic ref. Here, the referenced variable is atomic. We have essentially the same specialization such as for stood atomic, except the smart pointers. This meaning reading and writing of the reference object is no data race. This is the key point here. As always, the lifetime of the reference object must exceed the lifetime of the stood atomic ref. And, okay, this is what I already mentioned. Let me show you an example. No, this was wrong. Let me show you an example. Here I have a data type. And for some reason, it's expensive to copy. For some reason. And I want to increase this counter concurrently. And here's what I did. I have a function count, which has a vector of threads And then I make a atomic ref to this counter here, you see? This is what I want to protect. And now I start 10 threads. Each thread takes counter by reference and gets one number between 100 and 200 and increments this counter this amount of times. And at the end, we have 1591. This is just the number. And this is thread safe. This is not a proof, but let me show you something. When you do concurrency, I strongly suggest that you always use thread sanitizer. Well, let's wait a few seconds. You see, it's not a proof, but we see at least that it's not red. But when I remove this atomic ref here and make it just an atomic, non-atomic, now we see a few colors. Come on, it's just running. You see, thread sanitizer kicks in. There seems to be a data race. Believe me, that this is a data race. Okay, let's jump back. We have in C++ 20 semaphores. Let me naively, let me do it differently. Requesting a semaphore decrements the counter, releasing the semaphore increases the counter, right? And here's the interesting point. The requesting thread is blocked if the counter is 0. I don't blame me for that. I often introduce a semaphore as a generalized mutex. A mutex has two states, locked, unlocked, false 2, 0, 1, how you would call it. What is the key difference between a mutex and a semaphore, which only has two states? A mutex, you have to lock. Exactly. So, therefore, I know what I talk about. I want to say, but this is how I use them. A thread must be locked and unlocked. A mutex must be locked and unlocked in the same thread, but not a semaphore. This is for me the key difference. And then we have two of them. We have a counting semaphore and one, let's say, an alias, which the number 1, which can only have the states 1 and 2, 0 and 1. This is what you can do with a semaphore. You can ask how the maximum value of it. You can release it by default by 1. You can acquire it. You can try to acquire it. This may be successful or not, we don't know. And you can also do it with a time duration or time point. These are the data types you have since C++ 11. Okay. Let's play once more. Producer, consumer. The same program such as before, you see. I say waiting for work, set data ready. But now I use a counting semaphore initialized with 0. It can at most have the value 1. So it can flip forwards, backwards from 0 to 1. And here's the guy who is waiting. He wants to acquire it. But he cannot do it because the value is initially 0. First, the sender has to release it, put it from 0 to 1. And now the other guy can continue. I'm a big fan of semaphores because for me they are extremely easy to read. You will see what I mean when I talk about condition variables. Okay, and I forgot to mention it. They are for me also unbelievably fast. This astonished me a lot. I will show you a few performance numbers in a few seconds. When we play ping pong. Okay, let's jump back. And now to my favorite in C++ 11. I gave around 2015 a few talks, which I called threads and locks must go. I should have called them condition variables must go, but anyway, this is what I essentially mean. Condition variables. Okay, their model is pretty simple idea. You want to have a producer, consumer, sender, receiver workflow. An extremely simple idea, synchronization of threads, right? Okay. You have a sender, which says notify one or all, and you have a receiver, which waits for it, using the same condition variable. You can wait for it without a time limit or with a time limit. To make it short, always when you use for, you need a time duration. When you use until, you need a time point. Just remember it. This holds for all C++ data types. Okay. The fun starts with these 3 points here. Now let me explain a story. This is a German story. I don't know if this applies to Norway, but you can imagine. Imagine you lay in the bed. So let me put it differently. Condition variables can be victim of 2 serious issues. Spurious wake up, lost wake up. What does it mean? You are sleeping and you wait for the alarm clock to go because you have to stand up. Then you are for some reason awoken. But it was not the alarm clock. It was the cat scratching at the door. We call this a spurious wake up. Some event happened and you think this is now your time. What do you do when you are in bed? Don't do anything with the cat. So what do you do? How can you be sure when you stand up, it's the right time? What do you do? Exactly. You need an additional predicate which you can check, which gives you the answer true or false. In this case, the clock would be fine. This is a spurious wake up. We have also, I will show it you in a few seconds, another issue, lost wake up. Imagine you go to bed after the alarm clock went. This is a dead clock, to be serious. You wait for something which will never happen. Because the standard says the wait call only recognizes a notification if it's in the wait state. But we do threading, we have no idea in which state it is. Okay. And here's the workflow. Once more, this is 11. Maybe the only reason I explain it to you is to say to you, don't use it. Okay, this is the wait flow. Now I explain the workflow based on the waiter here. This is my wait call, and this is my additional predicate, you see? Here I check if something happened before the notification. This is, I have to establish a memory. So I wait. I first check when I go into the wait call. I wait while locking the mutex. I first check if return rapidly happened. If this happened, the alarm clock went before I went to bed. If not, I'm in the wait call and I fall asleep. I go to the kernel modus. I release the mutex because this guy wants to have it. And I sleep. I sleep. And then at one point in the future, I got a notification. I lock the mutex once more. I check first if return ready is set. Assume it's not set, therefore I know it was the cat. And then I fall back once more to sleep. Sleep. Notification. This time the predicate, the return ready is checked. And therefore I know it was not a cat. I have to stand up. I have to go to work. It's really fun to explain this workflow. And you have to essentially do it in this way. You have to check something which happened before. If this is a Boolean or a vector, you put something in. I don't care. but you have to build your memory. If not, you are really, how should I say it? It's extremely likely that you will get a lost wake up. I'll show you to you in a few seconds. This is the same workflow such before, no? Waiting for work, set data ready. I started intentionally waiting for work first. But here I would have a lost wake up. Have a look here. Here I first, the alarm clock goes before I go into wait state. This would be a lost wake up. Deadlock. And here's what I do. It's essentially the same workflow. Waiting for work has a critical section, uses this mutex here, locks it, and waits, having this predicate, checking this predicate. And this is my set data ready. Here we have it. Notify 1 is thread safe, therefore I put it outside of the critical section. And now let me play a little bit. I only change now the probability of an issue. Let me do this afterwards. I cannot, okay, so far it's fine. And now let me remove this predicate. And now I can be a victim of a lost wake up. But we cannot see it. I will get here a timeout. You see the worker was first awake, then. At least one additional try. Now it looks better. I think this is timeout. And now I get a timeout. No, damn. Sorry, but believe me. When set data ready will happen first, I have a timeout. Sorry, I have deadlock. Only one additional try. In the hotel room it worked. But this is the fun about threading. Now it looks better. This is a timeout, this is a deadlock. And Matt Gottwald threw me out of the compiler, essentially. Sorry, Matt. Okay. You see, I'm a big condition variables fan. And now to my final example. I want to do a ping pong game. Because when I recognize there are so many ways you can synchronize threads in 20, which one, I always ask two questions. Which one is the easiest one to use? Which one is the fastest one to use? I have here already the numbers. I will not prove the numbers. You have to do it on your PC. But I have these examples, say run on the compiler explorer, except this guy here, it takes too long. You have it. Let me explain my ping pong game. Let me do it here, just by reading it. One thread executes a ping function, and the other thread a pong function. The ping thread waits for the notification of the pong thread and sends the notification back to the pong thread. The game stops after 1 million ball changes. And I measured just how long this 1 million ball changes take. Here's the program. Once more, this will not work, but I can reduce the number. You see, let me remove a few zeros here. It will work locally, but here I got a timeout. You see, now it works at least. So I have a ping thread and I have a pong thread. I have to be precise. I have a thread T1 executing ping and a thread T2 executing pong. What is the ping thread doing? It does its job 1,000 times. Then it logs a mutex, checks if data ready is false, sets data ready to true, increments the counter and notifies the other guy. And another guy essentially does the same, but the opposite. It logs the mutex, checks if it's false and sets it to true. Hi, sorry, this was wrong. Here's the other guy. Sets it to true, checks for true, and sets it to false. So exactly the opposite. This one waits on condition variable 1, and this one notifies on condition variable 1, and the other way around. It's essentially, you could do it in one function, but this would be a little bit of a mess. And 1 million ball exchanges. And you see, well, this looks not so easy, but you can achieve it. Now I do it once more with an atomic flag. And now I can do it 1 million times. You see, it works. 1 million times. And here I do it differently. This is my ping thread. Initially, my atomic flag is false. Therefore, this guy can continue because this blocks when it would be true. So it continues, it sets it to true, and then it notifies the other guy. The other guy waits on false, clears it, which means it puts it to false, and notifies back. It's essentially the same, but symmetrical. But you see, there's no need here for using a mutex, log, don't care about spurious wake-ups, lost wake-ups. It's fine by design, or correct by design. This is atomic flag, but I can do it even with an atomic bool. I could also use 2 atomic bools, but I will not show it to you. This looks pretty similar. Now, and I have to say it, here I measure time and here I measure time. Now, I have an atomic bool, initialized to false. This means this guy can continue because it blocks on true. It puts it then to true, increments the counter and notifies the other, and the other is waiting on false, you see, the opposite, and puts it instead of 2 to false. Essentially, almost the same workflow as the previous one. And now the last one, which is semaphores. This was the wrong one. Semaphores. Don't believe these numbers. On a local machine, they work differently. So, semaphores. This is easy. I have a semaphore. I have 2 semaphores. Both can have the value 0 or 1. I initialize them with 0. So you can flip from 2 to 1, 0 to 1, forwards, backwards. Then I use 2 semaphores. One for acquiring, one for releasing or for notifications. And this is what I essentially do. First of all, both are 0. Then I say here, release signal to ping. This goes now from 0 to 1. This means, what was the name? Signal to ping. Signal to ping. This is this guy here. This one can acquire it. It acquires it, it goes to 0, but now it releases another semaphore. Therefore, it goes from 0 to 1 and forwards, backwards. Now I improvise. What kind of synchronization do you prefer? Not from the performance point of view. I know you care about performance. From the usability point of view. The atomics, semaphores, or condition variables. What do you think is easier to get? I also like this kind of, but anyway. For me, this is crystal clear to this acquire release. But anyway, at least we can assume or we can conclude that we don't want to use condition variables. And here are the performance numbers. On Windows, this is a real PC and this is virtualized. But you see, always condition variables are really, really bad. By the way, when I show you performance numbers, always with maximum optimization. And you see, No, there's no point here. I don't see a point here. There's a reason for that. Once more, I cannot execute it on compiler exploit because it's too slow. I got a timeout. I did it locally. I did it first with the Windows compiler. Windows compiler supported these new things first, and then 2 years later, GCC supported it, and I used GCC. So I would say is there a use case for a conditional variable anymore in C++20? Do you know anyone? There's conditional variable any, which can do something special, but not conditional variable. So there's no use case, we agreed here, for conditional variable. Okay, we also get latches and barriers in C++20. It's a pretty easy synchronization mechanism. You have a synchronization point, and all threads wait here until a counter becomes 0. Okay, and we have it in 2 ways. We have a latch and we have a barrier. The latch is for the one-way iteration, the batch for the more than one-way iterations. And this is what you can do. You can say countdown, which counts down the counter by 1, by default by 1, but you can say I want to count it on more. You can say try wait, which is a terrible name, which just returns you if the counter is 0. I had a discussion with Dr. Volkmann, this is a terrible name. He wanted to fix it, but he didn't. He couldn't do it. It's a terrible name. You don't wait here, you just. Then you have a wait call. This returns immediately if the counter is 0. If not, blocks until the counter is 0. And then you have arrive and wait, which essentially does countdown and wait in combination. And by default, you count down by 1, but you can use a bigger value. Okay, let's do a simple workflow. I'm happy that this guy is not here. Wait a second. That this guy is not here. He's in the first room. Andre Alexandrescu. Okay, I have here a simple workflow. I have 6 workers. Herb, Scott, Bjarne, Andrew, Andre, and David. All of them perform this work here. What is the work? They perform this function object. They perform this operation here. I will say a few words about this in a few seconds. I did a simple standard cout synchronization. Forget about it. This is only for optical reasons. I will say more about it when I talk about synchronized output stream. I only want to be sure that this is nicely layouted. Okay, first, I display the name, and I say work done. And then here they have to wait. Each time a thread comes here, it decreases the counter by 1. And I forgot to mention some interesting point. This work down counter is 6 initially, and you have 6 workers, right? So each time someone is done, it decreases the counter by 1. When the counter becomes 0, all can go home and say see you tomorrow. And therefore, first all people prepare their work, and then they say see you tomorrow. Extremely simple, and of course not exception safe and so on, I know, but an extremely simple synchronization mechanism. And with a barrier, you can do it even better. This is a barrier. This is helpful for managing repetitive tasks. The interface is simple. You have a arrive call. You have a wait call, which blocks when the counter is not 0. You have arrive and wait, which is equivalent to calling arrive and then wait. And you have arrive and drop. This is a little bit a tricky function. Arrive and drop means that you are out in the next iteration of this loop. Therefore, in this situation, there are maybe 6 workers, and you say arrive and drop. I want to be a part anymore of the next iteration, which by default starts with the same number. And therefore, you can kick yourself out. I will show you an example. Now I have full-time workers and part-time workers. So the full-time workers work in the morning and in the afternoon. The part-time workers only in the morning. And this is, I have 6 of them, you see. In total, I have 6 workers. 3 full-time workers, 3 part-time workers. And this is what a part-time worker do. They do their morning work, and then they say arrive and drop. I want not to work at the afternoon. Therefore, the counter goes down from 6 to 3 because of 3 of them. But what the full-time workers do, they say not arrive and drop, they say arrive and wait. And then they have to fulfill the afternoon work. And this is a possible use case for arrive and drop. Okay, now we have here the same such as before. Okay, jump back. We have cooperative interruption in C++20. Why it is a bad idea to kill a thread? Go on. Do you have no idea in which? Yeah, of course, maybe the mutex is locked. Would be a lot of fun when you kill the thread. You have no idea in which state the thread is, essentially. This is always nice. I think pthread allows it, and they always also mention you should not do it, which is nice. I'm not a pthread expert. Okay. What we do, we allow cooperative interruption. This means I can say to a thread, please stop. And the thread can say, I will do it or not. And I can only do it once. Cooperatively. It essentially consists of 2 components and a third one, which will come later. We have a stop token and a stop source. The stop token is something you copy. It's extremely cheap to copy, and you copy it into this running entity you want to request to stop. And the stop source states the stop request. And this is what a stop token can do. Can ask if its stop is possible and if a stop was requested. This mechanism is built in jthread, the improved thread, and in condition variable any. I want to say it explicitly, not condition variable any. And this is a stop token. On the contrary, we have the stop source. A stop source has a function get token. This allows you to create a stop token. Then it has function stop possible to ask if a stop can be requested, if source can be requested to stop. You can only do it once. You can ask if it already happened, and here you request the stop. Let me show you a simple example using a jthread. Jthread, let's say this stands for, it was first called eThread for interruptible, now it stands for joinable thread, but anyway. I should not say eThread, I should say iThread. Okay. Here I have a main function and 2 really, really long lambdas. Usually I don't write this long lambdas, but here I do it. Here I have a jthread, which is non-interruptible. And this is what it does. It has a counter, it counts up to 10. It sleeps for 1/5 of a second, and always says non-interruptible. Here I have a little bit of interleaving, but I don't care. And here I have a jthread which got a stop token, you see? And here it asked if a stop was requested. And if so, it just returns. Now I have the main thread which sleeps for 1 second and then requests both threads to stop. Only the interruptible thread will react because it has a stop token here. And therefore, you see what's happening. First, both threads run, interruptible, non-interruptible, you see. Then the request to stop comes, and only the non-interruptible continues until 10. This is a jthread, or interruption of a cooperative interruption of a jthread. Okay. I don't want to say it, but I assume this is based on that. I'm not sure. Not because I know what you mean. Promise has the function get future. Here we call it get token. But what is special is, now there's one extreme different point. A future cannot be copied. And this can extremely cheap be copied. Maybe it's more shared. I don't know it honestly. Goes more this direction. You agree? Maybe a shared future? Yeah, but it goes more in this direction. Okay.
Similar to anything like a shared point.
Yeah. Some sharing facility. I see it the same way. You can, by the way, go on GitHub. You look for Nikolai Sutu's implementation and study it. Because he created this guy. I don't get you.
You don't have to accommodate for exceptions.
Once more, if you want to know more details, you can see how these could be implemented. Okay. I played with this stuff before it was published or available because I'm really, really curious which direction C++ in concurrency goes. Okay. I was honestly a little bit disappointed about cooperative interruption. You can do it with jthread, you can do it with condition variable any. But then I recognized this is an extremely generic mechanism. I recognized it. And now I show you an example what you can do with that. And honestly, I like this example more because this is more explicit. You know Python? The meta rule of Python? The second meta rule of Python? Explicit is better than implicit. Code should be explicit, should know what's happening. And now you see it. Have a look. I have here stop source. I create my stop token out of it. And now I have a few running entities. I have a thread, which takes a function and a stop token. So if I can also use it as a thread. But now I have to use it as an argument. And what is function 1 doing? Here, it sleeps for 1 second and then it asks if a stop was requested. In this case, I just say stop requested, only to see what's happening. So I can do it with a thread. I can also do it with a jthread. I can do this explicitly. This also performs the function 1. But it's even better. I can do it with async. It takes my stop token, and here I ask if I was requested to stop. I can do it with a promise. This is my promise, which I move inside this thread. And now let's see what function 2 is doing. I registered here a callback, which is called when the stop request appeared. So I can register callbacks, which are called in case. You cannot only register one, you can register as many callbacks as you like, but you don't have to guarantee which one runs first. So it's an extremely generic mechanism, and now I like it, honestly. And I can also do it from the main thread, just for fun. You see? Here I request a stop, and then I ask in the main thread if there was a stop request. This makes no sense, but I only want to show you it's possible. And here you see all the reactions. And once more, I like this way more because this is extremely explicit. And I want to program explicit. You should read my code and you should know what's happening. This is readability is one of my key concerns. Okay. A few short remarks and then I'm almost done. You know, this is a lot of fun we have with std_thread. I don't show it to you, but because you know it. std_thread, I show it to you. You should see it. This makes it more obvious. Terminal called without an active exception. Program terminal with. With Microsoft, you only get a number, which makes it also not nicer. The point is the following. When you create a thread T, and this thread T goes out of scope while the thread is still joinable, why you never called detach or join on it, you get an std terminate in its destructor which ends with an abort. And this is what you can see. And what I mostly like about this error message is the following one. You have no idea what happened. This gives you no clue what happened. And this issue is gone with C++ 20. Then you should use jthread. And jthread joins automatically if necessary in the structure. And you see here now it's fine. Takes a little bit longer, but it's fine. No, it does not take longer, sorry. When should the exception be thrown once? Okay, fine. I answered the question, thanks. Okay, so this was, by the way, a design issue. The thread was created in 11, and all people said immediately, use a scope thread. I implemented, Anthony implemented, this was pretty easy, but now we have it. Or use the one we have in GSL. Now it's fine. Okay, and now to the last feature I want to mention in C++ 20, synchronized output streams. Standard cout is thread safe, but not in the way you think. And now you can have the guarantee that your sentence is written in an atomic step. Here are two simple examples. Here I have a std_cout wrapped in a sync_out. And now when I write to it, nothing happens. Even this std_endl call has no effect. The output is written when synced out goes out of scope, and this is exactly here. Therefore, the entire sentence is written in one atomic step. Oh, now let me a little bit picky. What idiom in C++ models synced out? What is the most important idiom in C++? The term goes back to Björn Stustrup and he hates it. RAII. Because you do an action when the thing goes out of scope. And here the action is you flush the buffer. You can do it this way or you can do it even this way. Now this thing lives until this semicolon here, and therefore here it's flushed. And this is what I should have used before. Diana noticed it. But when I created this program, this was not available. And now I'm done. But now it's available, by the way. Okay, this was C++ 20. I made a deep dive. I also gave you a little bit of background to say what improved regarding atomics in C++ 20. Yo. And 5 minutes are left, but anyway, I'm longer. I stay longer here if necessary. Any questions? This was what I essentially wanted to say. Go on. What do you mean exactly what atomic flag and spurious? Can you kick in, Daniel? Do you know it? We still fight. Yeah. I so far never use any kind of predicate when I would use atomic flag, because I assumed that it does not have the issues of spurious wake-ups. But on this level, you often have issues of spurious wake-ups, so I'm not 100% sure. You see, I explained you compare exchange strong. The weak thing could have spurious wake-ups. What's that? Someone is shooting at me. Statical. I'm on fire or on power. Okay, so it's a predicate by itself, which essentially checks atomically the state of the atomic with the value you. Therefore, it seems to be something here.
I will just hold it.
Now I can do it this way. Yeah, I'm really, really strong. Okay. No, I'm weak, but now I'm strong. So we assume this is fine. But usually you have to read the original wording. Okay, any additional question I cannot answer? Then we do it a different way. A question I could answer. Then I would say we are done.